All right, so here we go. So we're going to start by doing the last problem from chapter 7, which is going to be page 175, number 64. It is long. Okay, so Zoe was reading the problem, Casey. You couldn't hear her, but you had time to read the problem. So let's start with the picture here. All right, so here's going to be our conveyor belt. There's a part that goes up at an incline, there's a part that's horizontal, and then there's a part that goes down at an incline. Those inclines are 10 degrees. And then the length of each segment here is equal. And we've got some kind of box that's going to be moving through this set of conveyor belt segments. All right. So what kind of things do we know? Okay. And what else do we know? We know what the mass of the box is, right? Okay. And what are we looking for? We're looking for the power. Okay? And we're not just looking for any power, but we're looking by the power due to what force? The conveyor belt on the box. So what forces are going to make the box move along the conveyor belt? Maddie, a gravitational force. Well, why gravity? Doesn't make it move. Normal force. So what did you say before static? Okay, so we've got the normal force. So yes, the normal force may help move it along. And what other force, though? Be static friction, okay? And it's static friction because the box isn't moving with respect to the conveyor belt. It's like stuck to the conveyor belt, and the conveyor belt is pulling it, but they're staying together, okay? So we want to find the power due to the conveyor belt. And what kind of formula am I going to use for that? I could use that power is equal to dW dt, but then I'd have to find the work. What's another way that I can express power? F dot V. So it would be the force due to the conveyor belt dotted with the velocity. And I have the velocity. So if I'm going to be dealing with the force due to the conveyor belt, what am I probably going to have to do next? Free body diagrams. Okay, so we'll try to go down here, keep as much on here as possible. So for part A, I'm talking about when my block is moving up the incline here. So what kind of forces are acting on the box? Okay, so there's a gravitational force that's going to go straight down. There's a normal force. In which way does the normal force point? Perpendicular to the interface. And then what else? A friction force. Which way is that friction force going to point? Yeah, up the incline. And we decided it was static. And it doesn't really matter whether it's the maximum static friction force or not, because we'll talk about that in a minute. Okay? And it's going to point up the incline, because if there were no friction, what would happen to the box? It would slide down the incline. It does say specifically that it doesn't slide. Okay? Now, remember that over here, I'm taking a dot product. And what does a dot product do? It turns from a vector into a scalar, but it does it in a really special way. Okay, so I would have FC V cosine phi, but I'm trying to avoid that. I'm trying to, well, what's the other way that I can make a dot product? What's the other way I can express a dot product? Nope. Nope, that's the other way to express work, but we're not going to use integrals here. Yeah, but I don't want to use the cosine part. Remember that if I have A dot B, yeah, that's where we're going, is with unit vectors. What's the bx plus right. Okay. So what this means is that I only pick up terms when I have components in both directions. So, like, if there was no by term in my vector, this whole term would go away, and it wouldn't matter what the value was for A in the y direction. So my velocity vector up here is only in a very specific direction. So I'm only worried about what the force due to the conveyor belt is going to be in the same direction as the velocity. Okay, so I'm going to draw the velocity into my free body diagram, although it's not really there because it doesn't belong there. Okay. And if we orient our axes so that x is up the incline and y is perpendicular to the incline, then I only care about the components of the force due to the conveyor belt that are parallel to the velocity, right? Okay, so what force due to the conveyor belt is going to be parallel to the velocity? Yeah, the static friction force. Okay, so if I can figure out the static friction force, that's what I'm going to put in here for FC. Well, eventually I'm going to have to find out what that static friction force is. And being that I haven't been given what the coefficient of friction is, I may have to use some other information such as the components of the gravitational force to figure out what Fs is. Okay. So that's a really good point. How are we going to figure out what Fs is? Okay, so I can use F net equals ma. Okay, so I've got F net is equal to ma. My speed is constant, which we talked about before. So that means that F net will be equal to 0. And what direction am I specifically interested in? X. Okay, so I've really got F net X is going to be equal to 0. And what are my forces in the x direction? So I've got Fs, and I have a component of the gravitational force. And I can break that down here like this. so that this will be FGX. Okay. So FS, positive or negative, FGX, positive or negative. So I can see that FS is going to be equal to FGX. And now we have to play that game with the angles. So I can kind of extend my triangle here. And what's this angle here going to be? 10 degrees. So that means this angle up here is 80 degrees, which means this angle here is 10 degrees. Okay. So FGX is going to be equal to what? MG sine what? 10. Which I know. I know what MG is. I know what M and G are. I know what the sine of 10 is going to be. So remember that my power was FC dot V. And my V is only in the X direction, so I'm only going to pick up the force of the conveyor belt in the X direction. So basically that's going to give me FSV. We could put in a cosine phi there, because what's phi going to be? 0, okay? And so the cosine of 0 is equal to 1. So the power is going to be mg sine 10 times v. We can substitute that all in. We have 2 kilograms times 9.8 meters per second squared times the sine of 10 degrees. Make sure you're in degree mode. And then what? The velocity was 0.5 meter per second. Yes. So what are we going to get for the power? .7 what? What? Watts is what I'm looking for. Is that what other people got? Okay, Gianni confirms. Okay, you with me? We got it? And that was only part A. All right. So part B is the part of the conveyor belt that's horizontal. So the velocity is going to go that way. And again, I want to find the power. It's still a constant velocity, so I can still do Fc dot d. And again, if I'm looking for Fc, which is a force, I'm going to want to make a what? Free body diagram. Zoe, did you have a question? Oh, I'm sorry. Dot. I wrote the right thing. Thank you, though. Okay, so what are the forces going to be that are going to act on my box? All right, there's going to be a normal force. And what else? Gravitational force. Is that it? There is no friction force, which is, Sari does not like that there's not a friction force. I can see it. It's not moving, right? And there is no force to go against it. So really, the one way to think about why it keeps moving is momentum. Is that when it reaches the top of the conveyor belt here and then goes over, that it has a certain velocity. And as we'll talk about in chapter 9 when we get to momentum, an object will, it's also Newton's first law, an object will keep doing what it is doing. So if that crate or box is moving at 0.5 meters per second and there's nothing to stop it, then it will keep moving at 0.5 meters per second. Is there energy, are there things going into making the conveyor belt move at 0.5 meters per second? Yes, but we don't care about those things because we're interested in the power that the box feels due to the conveyor belt. Sari's nodding now. I'm still not sure she believes me, but she's nodding. So, what's the power going to be? 0, says Maddie, and she is correct. Because the force due to the conveyor belt is going to be what? No. There is. Is the box falling through the conveyor belt? It's the normal force. But the normal force is not, as Maddie said, in the same direction as V. We can also look at this as NV cosine theta, or phi, whatever you want to call it. But what's that angle going to be between N and V? 90 degrees. And the cosine of 90 is 0. Okay? Makes sense? All right, so we still have part C. So in part C, what's happening? Right. So now in part C, my incline goes this way. Here's my box. Again, I'm looking for the power that I'm going to get from the force of the conveyor belt on the crate as it moves at that constant velocity. If we make another free body diagram, what are the forces acting on my crate? There's going to be a normal force. Yes. And what else? Gravitational force. Now this is the mirror image, it's the flip of the free body diagram that we had when the crate went up the incline. Okay, so again, I'm going to draw in the velocity even though it doesn't really belong here. And what's the force from the conveyor belt that has at least a component that's parallel to the velocity? The static friction. So again, all right, so again, we can, hang on, Zoe. So again, it's going to be the static friction force dotted with the velocity. But now the direction of the velocity and the direction of the static friction force are 180 degrees apart. And we know that the cosine of 180 is -1, so that's going to give us negative FSV, or the power will be negative 1.7 watts. We don't even have to figure it out again. All right, we good? We got it? Okay, that's really the end of chapter 7. And now we're ready to start chapter 8. Okay, which is the continuation of energy. And chapter 8 is a little longer, but we will continue to deal with energy. All right? Yes? So Sari wants to know where FG goes in this part of the problem. FG? Why would I put it in the diagram? Because it's a free body diagram and I should include all of the forces, whether I'm going to use them or not. Because the forces that are in this free body diagram are the only forces that act on the block. I told you you didn't like my answer before. What are you worried about? All right, Maddie helped Sarah figure out what she was confused about. All right, on to chapter 8. So, chapter 8 starts with potential energy. We did talk about potential energy freshman year, so if you had physics with me or you had physics with Mrs. Elias, it was something that we talked about. Potential energy is often described as stored energy or the ability to do work. But the way I like to think about it, other than stored energy, is it's the energy associated with the arrangement of a system of objects that exert forces on each other. So it's the energy associated with the arrangement of a system of objects that exert forces on each other. So if this is going to be energy and there are going to be forces involved, what should that make you think about? Work, because work is what? Yes, work is the change in kinetic energy, but work had its own definition. And then later on, we use that definition to connect work to a change in kinetic energy. So work is the transfer of energy between objects using a force. So what I have here are a system of objects that interact using forces, and there's going to be some energy associated with that. So I have to be able to associate potential energy with work. Now, for a lot of reasons that'll make sense in chapter 9, the symbol that we're going to use for potential energy is U. P is power and P is momentum. Zoe's burying her head in her hands. She's beyond disgusted. We have to have a little commentary here, because Casey would smile. All right, so you just got to accept that it's U. I will occasionally cave and write PE, the letters capital PE, but your book will use U. The AP exam may very well use U, so you need to be familiar with that and accept that. So what we end up with is that the change in potential energy is equal to the negative of the work. Now you will of course ask yourself, why is there a negative sign there? Well, somebody brought up a couple of minutes ago that work is a transfer of energy and that work is also equal to the change in kinetic energy. And remember that the change in kinetic energy is K final minus K initial And if K final is greater than K initial, if the object is gaining kinetic energy, then the work is positive. But the question is, where does that kinetic energy that the object is gaining or that the system is gaining come from? Where does that work come from? Where do you think it's going to come from? Potential energy. There will be forces involved, but it's going to come from potential energy. So if my increase in kinetic energy means positive work, that means that if I'm increasing my potential energy, I'm going to have to decrease my potential energy, and that's going to be a negative amount of work. Well, it'll actually, let me take that back. If I have, I'm just going to leave it where it is. I'm going to do an example and it'll make more sense. Okay. Well, let's go from here. So if my object is increasing in kinetic energy, the work is positive. If the work is positive, that means that delta U has to be what? Negative. It has to be less than 0. So that means that U final minus U initial is less than 0, which means that the object is losing potential energy, and that potential energy becomes the kinetic energy that the object gained. Okay, makes sense? Sorta, kinda. It's only the first page of notes. All right. All right, everybody got what they need? Okay, so let's compare this to the example of tossing an object up in the air, because we've already talked about this and what happens. Plus, you know what happens. So if I have some kind of ball and I toss it up, it's going to go up to here. What's going to happen at the top of the path? It's going to stop momentarily. And then what's going to happen to the object? It's going to fall back down, back to where it started. Okay. On the trip up, what do you know? Oh, go ahead, Maddie. Go right ahead. I don't know what will happen to the temperature if we close the door, but there is a lot of noise. So we'll see what happens. If we have to open the window, we'll open the window. There we go. All right, so as the object rises from the initial spot where I toss it up to where it pauses at the top, what's happening to the kinetic energy? It's decreasing. So the kinetic energy is decreasing. So that means that K final will be smaller than K initial. So delta K has to be less than 0. So what does that tell me about the work? The work has to be less than 0. And in fact, based on what we did in Chapter 7, you know what that work is. Or you could figure it out. What's work equal to in general? What's our favorite equation for work? F dot D. What's my F in this situation? The force of gravity. How do I write the force of gravity? mg, mass times g. Which way does the gravitational force point? Down towards the Earth. Which way does D point? Up. So D and FG, what's the angle between them? 180 degrees. And if we remember that I've got this, that's going to give me FGD cosine theta. So I've got MGD cosine of what? 180, which is -1. Okay, so that work is going to be equal to negative MGD. So, if the work is less than 0, what can you tell me about the gravitational potential energy? Or I'm sorry, the change in potential energy. That's going to have to be positive, which means what is happening to you? Increasing or decreasing? It's going to be increasing. Okay. So if we look at the trip down now, what's going to happen to the kinetic energy as the object falls from the top down to its original height? The kinetic energy is going to increase, so that means delta K will be bigger because K final will be bigger than K initial. What does that tell me about the work? It's going to be greater than 0. And what does that tell me about the change in potential energy? Less than 0. Which means that the potential energy is doing what? It's decreasing. Because it means that U final is smaller than U initial. So we've got this interplay here that we'll come back and talk about later in chapter 8, where as the kinetic energy is increasing, the potential energy has to decrease. And when the kinetic energy, I'm sorry, I said that backwards. When the kinetic energy is decreasing, the potential energy is increasing. When the kinetic energy is increasing, the potential energy is decreasing for the system that we're talking about. Okay? We got it? We good? All right. So let's generalize it about the things we want to talk about when we do this. So I'm going to define a system. A system is 2 or more objects. A force acts between a particle-like object and the rest of the system. So a force acts between a particle-like object and the rest of the system. If our system is the ball and the earth, then the ball is the particle-like object and the earth is the rest of the system. And what's the force that acts between them? The gravitational force. Okay. Everybody got 1 and 2? All right, number 3 is kind of long. So, when the system changes, and that usually means that the arrangement of the objects changes. So the ball is getting farther away from the Earth, or the ball is getting closer to the Earth. This force does work, W1, on the particle-like object. Transferring kinetic energy, I'll just read my notes. Transferring energy between the kinetic energy of the object and some other form of energy of the system. So when the system changes, this force does work, W1, on the particle-like object, transferring energy between the kinetic energy of the object and some other form of energy of the system. So if we're talking again about the ball that gets tossed up in the air, the ball's kinetic energy changes, but at the same time, the potential energy of the whole system changes in response to that change in kinetic energy. And finally, point 4, when the configuration is reversed, the force reverses the energy transfer. Doing work, W2, in the process. Everybody got it? Okay, so again, if we're talking about the ball-earth system, like we said, it's the gravitational force that acts between them when the ball rises. And that gravitational force does some work, W1 equal to negative mgd, like we had on the other screen. And the kinetic energy is transferred from the ball to the system, and the potential energy of the system changes. When the ball falls back to the Earth, that work done is positive mgd, and now the ball is gaining kinetic energy, and the Earth ball system is losing potential energy because it's being converted to kinetic energy. Okay. So take a look for a minute at what W1 and W2 are. because in this situation, we know that W1 is the negative of W2. And we know that that work done is equal to the change in kinetic energy. But we also know that that work done is equal to the negative of the change in the potential energy. So we have this situation where all of the changes in the kinetic energy are balanced out by changes in the potential energy. But this only happens when we have a special kind of a force that is responsible, that's acting, that's being exerted to make these changes. So what's the force in this situation? So it's the gravitational force. And based on your reading, what kind of force is the gravitational force going to be? A conservative force. What's the other kind of force? Non-conservative force. So for a non-conservative force, that change in kinetic energy is not going to be equal to the negative of the change in potential energy. So what's an example of a non-conservative force? Based on your reading, perhaps. A friction force, kinetic friction force, actually. Okay, if I have the ground and I have some block and this is a friction-full surface, so there's going to be friction. If I give the box a push so that it has some initial velocity in that direction, so it's got some initial kinetic energy, right? That's not equal to 0. What's going to happen to the block? It's going to slow down and come to a what? And come to a stop, where its final velocity is 0 and the kinetic energy is 0. So the kinetic energy changed. There's a delta K. But where did that kinetic energy go? It went into heat or thermal energy. To go back to those statements we wrote before, this is some work 1 that the force has done. Okay. But those statements that we said before said that if I reverse the process, so my object starts over here with some initial velocity and moves that way, what's going to happen to my block eventually? It's going to stop. It's in the same position that it was in before, but did it regain the energy that it lost to kinetic friction? No. Okay. So when energy goes to thermal energy, it's gone forever. Not really, because energy is conserved, and we'll talk about that. But it's not going to come back. It's more dramatic when I can kick garbage cans across the floor, but in case you can't see that, so I have to draw pictures. Okay. So I want to talk about one more thing, and then I'll let you have a little break. All right. So how do we tell if a force is conservative or non-conservative? Again, it was in the reading. Right, or the closed path test. Okay. So the closed path test says let the force act on a particle around any closed loop. It means that the particle makes a round trip and it ends where it began. If the total energy, okay, you got to add it all up. The total energy transferred to or from the object as it goes around the loop is equal to 0, then the force is conservative. So you might not realize this, but this is a really powerful result. It means that the work done by a conservative force on a particle by moving it between 2 points does not depend on the path that the object takes. So if I have the table here and I start with a block on the table and I lift it up and I put it up here, then I know that a certain amount of work has been done, a certain amount of energy has been transferred. Okay? Maybe I'm tossing it up, maybe I'm just lifting it. But that transfer of energy is the same when I take the direct path as it is if I take a path that takes me all the way down here, maybe down to the main office, and then back to that spot. The same amount of work has been done. The same amount of energy has been transferred. All I care about, as long as it's a conservative force, is where my object starts and where my object ends. The same amount of energy was transferred as long as it's a conservative force and my object begins and ends in the same spots. So this particular example is a little crazy. But think about the marble roller coasters that you made freshman year when you took engineering with me. If you want to know what the speed of the marble is going to be at the end, all you really need to know is how high it started and how high it ended at. And whatever potential energy was lost got converted to kinetic energy, and that'll give you the speed of the marble. Okay? It doesn't matter how many loop-de-loops. It doesn't matter if it went up and down. It doesn't matter the curves. All you need to know is where it starts and where it ends. Because the force that you're working against, or the force that's doing that work, is the gravitational force, and it's a conservative force. Okay? All right, so let's take a little break here, and then we'll come back and we'll calculate some actual potential energy values.